my name is Jessie Lynch, and I'm a part of the GOLD team. Our goal was to create a spinal cord cell therapy plant. Spinal cord cell therapy is a growing need. There are over 250,000 people in the U.S. alone that need spinal cord cell therapy to even be able to walk again. And 12,000 people are added to this list each year. The goal of our plant was to make between 20 and 30 batches each year. And we were able to actually make 27. Our plant is located in the Northeast. Next, you will hear from our other members about our plant and the economic evaluation that we came up with and whether we recommend following through with our design or not.
Good evening, folks. Today I will go through with you on a small block flow diagram overview of our cell therapy operation. Our first step of the operation is thawing and expansion, where we will put the cells up to their maximum growth temperature of 36 degrees Celsius, which will then be put in an expansion reactor with media for the cells to reach their maximum growth capacity in a batch operation. Our next step is purification and differentiation. We will centrifuge out the media before the cells are put into a differentiation reactor, given growth factors which will turn the stem cells into neural cells for our final product. Our next step is concentration and separation, where we will use microfiltration and ultrafiltration to take out other impurities and media, and then separate the cells based on if they're differentiated or not. Our next step is product formulation and purification, where we will put the cells into a mixer with respective DMSO and serum to achieve the composition necessary for packaging. And then we will separate out the formula into 5 milliliter vials before they are frozen to negative 80 degrees Celsius for further packaging.
Hello, my name is Sean Baista, and I'll be talking about the first step in our process. The first step of our process is the thawing of the cells. The cells will be cryogenically frozen at approximately negative 112 degrees Fahrenheit, and the cells will need to be thawed to approximately 97.8 degrees Fahrenheit. We selected a water bath to achieve this heat transfer. The water bath will allow us to place the vials in the cells directly into the bath. The bath will operate at the desired temperature of 97.8 degrees Fahrenheit. Since the weight of the cells are order of magnitude smaller than the mass of the water's bath temperature will stay at constant temperature as seen in our QT diagram. The standard procedure for thawing will be placing the vials in the water bath for approximately 1 minute to allow adequate time for the heat transfer. Furthermore, operating at 97.8 degrees Fahrenheit will prevent hyperthermic damage to the cells, because the maximum temperature the cells can achieve will be the operating temperature of the bath, which is 97.8 degrees.
Now to explain our expansion reactor. One batch is defined as 100,000 cells being converted into 6.55 e to the 9th cells, which is based on the doubling time. Based on their doubling time, this one reactor will take cells and make the 6.55 e to the 9th cells in a time of 320 hours, and the cells need media and oxygen, and they're also releasing CO2 from cellular respiration, so that is exiting our expansion reactor as that happens. In total, the volume of the media and the cells reaches 15.5 liters, which is how we ended up sizing our reactor. It's run in a batch operation, and the cells need around 0.2% of dissolved oxygen and cannot exceed 0.21 pascals before shear stress ends up damaging the cells. So this reactor was run at 37 degrees C and atmospheric pressure to ensure that the cells would not be damaged.
Alright, the third operation in our process is centrifugation. This centrifuge is designed to move the stem cells from the proliferation reactor's mesh. We wanted to minimize the operational time of this operation to reduce the time between the differentiation and the proliferation step. At the same time, we also want to keep the RPM of the centrifuge low enough to not cause damage to the cells. To size the centrifuge, we use a sigma analysis to determine the proper rotating speed of the centrifuge. The sigma factor was calculated to be 5,070 feet squared, and using the dimensions of our whole centrifuge, the RPM was calculated to be 3,431 revolutions per minute. This speed is within our range of 5,000 RPMs to prevent cell damage.
Undifferentiated or incorrectly differentiated cells are separated from the successfully differentiated neural stem cells using a flow cytometry cell separator with a separation purity of about 98% and productivity of 6,000 cells per minute, running at 60 psi. The operation time per batch is about 295 hours, using one cell sorter. The cell sorter works by sending a stream of the concentrated cells with media and a laser to detect the impedance of the cells, and then they are deflected using deflection plates and sent into different fractions based on the charge. Assuming the bulk of the cells are either neural stem cells or human pluripotent stem cells, they can be identified by specific cell markers with fluorescent lasers and differences in cell conductivity. Over here, our signal-to-noise ratio of these antibodies or proteins are high in the pluripotent stem cells and low in the neural stem cells. Or over here, they're the opposite, high in neural stem cells and low in the pluripotent stem cells. These can be found and identified in the flow cytometer, and so this could be a method to separate out the differentiated cells from the undifferentiated cells. The purpose of our differentiation reactor is to provide cells that are undifferentiated with the appropriate amount of hormones and signaling molecules to cause them to differentiate into our neural stem cells, which we are trying to achieve. The conditions of the reactor is at 36.5 Celsius and atmospheric pressure, and it requires a total of 17 days for an entire batch. And it is run isothermally, and the reactor volume is 15 liters, mostly due to the media. So what we're trying to do is turn the pluripotent stem cells into neural stem cells. This is done with a neural induction media, which contains nutrients and supplements, and also specific hormones and signaling molecules, such as epidermal growth factor or FGF2. Each step, which I will go into next, requires different supplements and growth factors. There are 3 steps. The first one is the embryoid body formation. These are aggregates of pluripotent stem cells. This is done simply in suspension in a bioreactor with the media placed in the bioreactor. The next step is the neural rosettes, where we form 2D neural rosettes using microcarriers. This step requires the cells to be attached to a surface, and so we would use, in this case, a microcarrier which the cells would attach to increase the surface area and allow the formation of the neural rosettes. And finally, once those rosettes have gone through an appropriate amount of time, we would disassociate them with a dissociative reagent, and we would leave the neural stem cells in with specific supplements and growth factors such as the EGF over a few days, and our batch would be complete and it would be ready to be sent to the filters and separator.
We will now explain the key design parameters for a filter. We have 2 filters, a microfiltration system and an ultrafiltration system, which are basically tubular operations where the flow will go through these filters with a pore size of around 0.45 microns, which will then filter out the media and the water selectively while keeping the cells, because the cells are around like 10 nanometers in diameter. So basically the flow goes through and there becomes a cake resistance with the cells pushed up against the filter. This happens to be osmotic pressure because the bulk is a lot more concentrated than the feed. So it ends up going in opposite direction of being filtered, but since the cell density is so small, this is very negligible. So basically the water and the media are small enough to go through these pores while retaining the cells. And now if you look at the basic flux equation for our filters, Our filters operate at a flux of 0.02 meters per second, and this is based on Q divided by A, which has units of meters per second, and this is also equal to the driving force divided by the resistance. The driving force for this operation is delta P due to cross-flow filtration. Osmotic pressure is negligible due to low cell density, and then we have viscosity and the resistance of the membrane. Viscosity is around 1.2 centipodes, and the membrane is 10 to the 10th, 1/meter. So basically, the Q is dependent on the time of the operation. So if your operation is time dependent, Q is relatively set. But the area can be used to modify the Q. If it's put over into the top of this equation, the bigger the area that you have for your filter, the more flux that you can put through your filter, resulting in a less time for separation. Now on to product formulation, where we will have a mixer which combines DMSO, serum, and the cell input. These compositions are necessary for the 5 milliliter vials, where 3 milliliters of that will be cells, 0.2 milliliters of that will be serum, and 1.8 milliliters of that will be DMSO. This is achieved by feeding DMSO at a rate of 5.22 kilograms per hour and a feed of serum at 1.81 kilograms per hour. This product then goes to the cryopreservation step for further cooling and packaging to formulate the final product.
Alright, the final step in the process would be the cryogenic step. It's the cryogenic process of freezing the cells again to a negative 112 degrees Fahrenheit. And freezing the cells to this temperature will reduce all the biological processes that can happen and preserve the cells for storage. The standard protocol for freezing the cells would be freezing them at approximately 3.6 degrees Fahrenheit per minute. If the rate is too slow, the cells will die from dehydration effects, and if the rate is too fast, the cells will die from internal ice formation. For this operation, we chose the Cryomed control rate freezer. The freezer is programmed to automatically change the temperature in the system when the system achieves a thermal equilibrium by adjusting the flow rate of the liquid nitrogen into the chamber. With this equipment, we will be able to set the freezing rate to the desired 3.6 degrees Fahrenheit per minute, and be able to automatically program this. This will prevent any deviations away from it causing the damage. After freezing, the cells will be transferred to a storage tank, which will be maintained at negative 112 degrees Fahrenheit, which will be maintained by the vapor phase of liquid nitrogen.
Hello, my name is Jordan Janin, and I'll be talking to you today about our capital estimate for our stem cell production plant. First, we will start with the inside battery limits, which include the equipment costs for each one of our unit operations. As you can see here, we've listed out each one of our costs for the specific unit operations, and the highest cost we'll be facing are the bioreactors for the growth and differentiation of stem cells. These are relatively high because there are certain specifications that must be met within these reactors, so these incur higher costs. And also the freeze-thaw module is relatively expensive also because the integrity of the stem cell product must be maintained, and this requires a higher cost of the ending product. Next, we will look at outside battery limits for the stem cell production plant, and these include site development and utilities and other environmental factors that go into building this site. As you can see, the site development and utilities are high in this cost, and this leads to a total amount of $10 million and also a TCC of about $13 million. And going down the list here, we have total cost and other costs that must be incurred, so this results in a current point estimate of about $15 million. And also looking at an escalation of 13% and also a project contingency of 20%, we're looking at a total cost of our plant of about $20.6 million. The operating cost for the base case for the plant consists of costs for raw materials, utilities, and fixed costs. And each one of these is calculated based on the cost of each raw material per vial of cell produced. So first we start with raw materials. And as you can see here, we have cells, media, oxygen, DMSO, serum, and vials for the product. And looking at these prices, the serum cost is the most expensive because there are not many commercially available serums for the final product. But as stem cells production becomes more popular and more technology released, we feel that this price could be driven down, which would drive down our total raw material cost. Also, the vials for the stem cell product are still very expensive because they need to keep the integrity of the stem cell product intact as they are shipped to wherever they need to go. Next, we will look at utilities costs for the stem cell production plant. As you can see, we have low pressure steam, power, cooling water, and waste. The cooling water is the most expensive here because cryopreservation of the stem cells require very low temperatures. Also, there is a substantial amount of waste coming from the stem cell production plant, so this must be taken into account when calculating utilities, as the waste must be sent to sewage removal, and this cost is relatively expensive because of all the chemicals that are involved with this. The fixed cost includes labor, overhead, repair and maintenance, property tax, and insurance. The labor cost that we'll be using is based off of 14 workers making $85,000 per year. The overhead cost that we'll be looking at is 1.5 times this labor cost, and this includes accounting and other non-labor costs. Moving forward, we have repair and maintenance, which is calculated as 1.5% of the total capital estimate, and the property tax is also based off of the capital estimate as 2.5% of this. And lastly, the insurance is also calculated based off the total capital estimate, and that's at 0.5% of it. As you can see, the bottom three categories are very high based on our total capital estimate of $20.6 million. So that is why these are taking up much of our fixed cost amount.
Next, we're going to talk about the economic evaluation for the cell therapy plant. Our cell therapy plant is bringing in a total of 27 batches per year, with a capital cost of about $20.6 million. This number was found using SuperPro prediction and our calculations for outer battery limits. We are selling it costs us about 3,385 cents per vial to do this, which is about $2 million a year in cost. But we're selling our product for a total of $59.16 million a year. For our economic evaluation, there were many assumptions that had to be made. All of our assumptions are listed here to my left. All this information will be used in our Excel file, which we made to calculate our total economic evaluation, seeing if our plant was actually profitable. But next, we have to talk about our price history and future of our prices. Unfortunately, other projects were able to do a 5-year analysis and average, but cell therapy is such a new design that there isn't much research done on it. So what we had to do instead is we had to get quotes from companies. These quotes, such as for media, oxygen, DMSO, and serum, which are used for storing our final cells so they can be shipped off, and our vials are listed to my left. You can also see what size we would be buying these utilities at, and raw materials, and what we're paying for them, and the companies where we got the quotes from. For the future of our project, it was very hard to come up with what the prices for these things would be in the future. Like I said, there wasn't much research being done on it, and there isn't much being done on it still. Using the prices shown on my last slide, we were able to develop a base case. From here, you can see that we unfortunately did not have an after-tax return, but we were able to get a net worth of about negative $15 million. We were aiming to get at least 15% after-tax return, but as you can see, we don't even have a value at all. What is an after-tax return? An after-tax return can be defined as a discount rate at which the sum of the after-tax present worth is equal to 0. So because our capital price is so great compared to the amount of vials per year we're making, we're not even getting a number. It's almost as if we were dividing a huge number by 0. But we were able to see that if we raised our cost of vials per year and doses per year, what it would take to get a 15% tax return. If we raised it to $112.80 per vial, or $11,280 per dose, which, keep in mind, our current price is $10 per vial and $1,000 per dose, we can get a 15% tax return. This is a lot more money, but obviously it is doable. But at this point, we would not recommend the plant being made. We didn't have an after-tax return at all, which we were trying to get 15%. We're not making much profit. So before that can be done, we need to change a few things before we can even consider to construct our plan, we need to change a few things. That's what these next 5 studies show. So first, I will talk about this study being done on the change in vial production. As this graph shows, if we increase the vial production, eventually it is possible to reach our 15% after-tax return. For this to be done, we assume that the capital cost didn't change, which is probably unlikely, but with future research, we may be able to increase the amount of cells being made, vials being made, all of that, doses being made per year, without having to raise the capital cost too much. So by this graph, it's important to note that we assume the capital cost stayed the same at $20.6 million. So to reach our 15% after-tax return, we need to make at least 741,618 vials a year. That is about a 1,253% increase of cells being made. So, for our next 3 studies, we assumed that our cell production had an increase of 8%. This is because we wanted to see if the after-tax return would increase as we change these next 3 studies, such as utility prices. We wanted to see if it was even worth changing it, and with our current information, the after-tax return number wouldn't change at all with these changing values. If we lower the utility prices, it's actually not possible to receive the 15% after-tax return. With that being said, you can change them all you want. We're not going to reach our desired amount to continue with production. Next, I'm going to talk about fixed cost. Fixed cost includes things such as number of employees, all of our insurance, and everything like that. Unfortunately, those values are dependent on capital costs and can't be changed, but the number of employees that we have can. So, we assumed that we had a total of 14 employees. This is because we wanted 3 employees per shift and gave us some 2 extra employees for in case of call-outs, vacations. We assumed this was a good amount of employees to have, a safe amount of employees. And an alternative study, we said that we could potentially lower the number of employees to about 9 or 10 employees. This gives 2 people per shift. Although we do not recommend it, it is possible to change that for the fixed cost. However, when we did the calculations, changing the number of employees to as low as 9 employees working a year did not affect our after-tax return at all. So at this point, if it doesn't affect it, maybe it costs a little more money, but we would still like to have at least 14 employees to help with safety precautions. Next, I will talk about raw material prices. As I mentioned before, there isn't much research being done on raw material. Not much in the past, not much for the future. We assumed in this situation that as prices increase, they all increase on the same level. So, as we change these prices, it can be seen in this graph that we still can't reach 15%. So at this point, it's not much. There's not much worth in changing the prices. It won't reach what we need to have done to reach our 15%. Our final study was to analyze what happens when we changed our capital cost. At this point, we went back to our base case. We're not assuming that we're making 8% more of our vials per year. We're assuming we're making our current amount. We tried to lower our capital costs to see if we can get an after-tax return, and if eventually it could actually reach our 15% after-tax return. So this graph shows that it is possible. If we lower our capital cost to a certain amount, this also reduces our fixed cost, which was a major amount of our money being spent. So, to receive our 15%, we have to lower our capital cost, which was at $20.6 million, to as low as $1.34 million. We strongly suggest doing more research to see if buying equipment from other companies, if this is possible. However, at this point in time, we do not recommend moving forward with the production of our plant. Although 2 of these studies showed a positive outcome of reaching our 15%, it was a huge difference. And the chances of that happening right now are very slim. However, we do suggest completing more studies by combining studies. Maybe looking at lowering the raw material, finding another alternative use for DMSAO and serum, while also trying to lower the capital costs and increasing the vial production per year.
And now I can go into further recommendations that will improve our processes. Basically, the batch operation is the most time-limited operation because continuous gets run, and the longest that the other operations are run are around 1 hour, which is nothing compared to 320 hours. So by putting 2 reactors in a parallel series, we can pump out 2 times the amount of cells, but we also need 2 times the amount of vials getting put into the product. By putting them in parallel, we can take these cells and make 2 times as much, feeding the continuous process 2 times as much, which leads to twice the production with just the cost of 1 extra expansion reactor.